We are talking about properties of rational exponents and radicals. And we are going to simplify the following expressions. In this case, we're talking about radical expressions. So we have to use our properties of radicals in order to try to get these in the simplest form. It would be great if we could plug this in a calculator and get a value, but in this case, we can't. But what we can do is we can find different ways to rewrite the radicand or the number that's under the radical. So 27, another way that we can write 27 is we can say that is going to be the fourth root of 3 to the third. We agree that 3 to the third is 27. And then we can still write the fourth root of 3. Another way that we can write this is because it has the same number on the radical, we can combine them under the radical because it's joined by multiplication here. So we can take the fourth root of 3 to the third times 3. In this case, we know it's 3 to the first. So we can go back to our exponent rules, and we can say if they have the same base joined by multiplication, then what we do with the exponents is we add them. So we can write that as 3 plus 1. So we still have the fourth root of 3 to the third plus 1. And then that's going to be the fourth root of 3 to the fourth. And we know that if we have the same number outside the radical and the same exponent in the radical, those cancel each other out. And then our solution for this one is 3 in the simplest form. Then we look at B. Here we see that we have the same radical. So we're taking the cube root of both the numerator and the denominator. So when we, like for this one, where we put them both under the same radical, we can do the same thing with division. So we can take the cube root of 250 divided by 2. In this case, that helps us out because we can actually do this math. 250 divided by 2, we know what the answer to that is. And so we have the third root of 125. And we know that the third root of 125 is 5. Or we can rewrite this as the third root of 5 times 5 times 5. And once we have the same number of matches, so under here we have 3 5s, under the radical we have 3 5s. Once we have the number of matches that's the same as the number that's on the radical, we can take them outside as just one answer. And so the answer for this one is 5. The next one, neither one of these can be reduced. And if reduced, and even if we split this, we're not going to be able to get exact answers. But that is what we're going to do. We're still going to split it anyway. So we're going to take the fifth root of 3 divided by the fifth root of 4. And what we're not happy with in this case is we don't like to have a radical in the denominator. So there's one thing that we're going to do is we're going to rewrite this 4 to get it the base in the smallest terms possible. So another way that we can write 4 is 2 squared. So 5, or the fifth root of 3, and the fifth root of 2 squared. So what we want to do in this case is we need to get the same number on the exponent that is outside. That's what happened in the same case over here. We had 4 the radical, 4 in the exponent. Here, another way that we can write 5 times 5 times 5 is 5 to the third power. So if we can get that the same, then we can get rid of the radical in the denominator. Well, how many more 2's do we need in the denominator in order to match the 5? Well, we have to get 3 more, right? So 2 plus 3 is 5. So what we're going to do is we're going to multiply the denominator by, still going to have the same radical, fifth root. We're still going to keep the same base, but now we have to get it 3 bigger. So we're going to say 2 to the third. Same thing here, 5. Because we're multiplying by 1, we don't want to change the value of this. We just want to change how it looks. So when we multiply this together, in the numerator, 2 to the third is 8. So 8 times 3 is 24. So then we get the fifth root of 24. And then in the denominator, well, the whole reason that we did this is so we can get 2 to the fifth. So 5 fifth root of 2 to the fifth. And in this case, we have the same number on the radical. That is our exponent, so those cancel out. We can't reduce the numerator at all, so we get the fifth root of 24 divided by 2. And that is the solution. That's in the simplest form. And now we're coming to the last example here. And we notice that neither one of these are going to work. We can't take the third root of 5, and we can't take the third root of 40. But maybe we can change one of these radicands in order to get it so that we can add these together. In order to add things together, we need to make sure that we have the same, the same term, or we're combining like terms. So if we can get the cube root of 40 to be some form of the cube root of 5, then we can add those together. So another way that we can write the cube root of 40 is we can say the cube root of 2 times 20. Okay, still haven't gotten there yet. Well, another way that we can break 20 down is we can say that's 4 times 5. So the cube root of 2 times 4 times 5. Well, we can break this down a little bit further because we can break the 4 down. So we can say the cube root of 2, and then the 4 we can write as 2 times 2, and then we still have the 5 under the radical. Now, we have 3 2's. That matches the number that's on the radical. And so we can take those 3 2's out front, and that becomes 2 to the third root of 5. So we've changed the way our second term here looks, so now we can rewrite all together. So let's change my color to the pen. 3, or the third root of 5, plus 2 third root of 5. So now we have like terms. The term that we're going to add together is the third root of 5 and the third root of 5. Here we have 2 third roots of 5, and here we have an understood 1, because that's the number in front. If it's not written down, we understand that that's the 1. So 1 plus 2, and that gives us 3 third roots of 5. And then this is in the simplest form.